All right, so now we're going to talk about tension force. So tension is a pulling force, specifically caused by an object such as a rod or chain or some sort of rope or string. So tension will counteract all of the opposite forces, which is usually in a downward direction. Take, for instance, a chandelier. So the chandelier is hanging from the ceiling. The chandelier's weight is pulling down, and the tension is counteracting that to keep the chandelier from falling. So that's another example of Newton's third law. Every action has an equal but opposite reaction. Okay, so a 12 kilogram bucket is lifted upwards with a constant velocity by a rope. What is the tension of the rope? So let's just do some basic tension examples. So we're being lifted upwards, keyword constant velocity. Remember, constant velocity means there is no acceleration, so the net force should also be zero. So if we look at it based on a free body diagram, if we're lifting a bucket upwards, we should definitely have a tension force. But we also obviously have the force of gravity, and since there's no acceleration, then the tension should be equal to the force of gravity to counteract that. So another way of thinking about it is if F net equals ma, well, there is no acceleration here, so zero. Let's take tension being positive since it's the one pointing up, and then Fg being negative. Remember, you can place Fg with mg, mass times acceleration of gravity. I do need to find tension, so I'm going to rearrange and solve for tension. So it looks like positive mg is equal to T. So my tension is going to be the mass of the bucket, which is 12 kilograms times 9.8, which would make the overall tension 117.6 newtons. Okay, so there's a simple problem. We have the keyword constant velocity, which should immediately make you realize that the net force should be zero, so we don't accelerate. Let's try almost the same example, but this time we are going to accelerate upwards by 0.6 meters per second squared. So think about what that means for your free body diagram. If we're accelerating upwards, think about the total net force. We should have an overall upwards net force. So if we're talking about tension versus the force of gravity should be smaller than tension. That way we do have an F net up, and we have an acceleration in the upwards direction. For this example, we do have F net equals ma. It's not going to zero out this time. Tension is positive, force of gravity is negative. So then we have ma equals tension minus, and I'm going to replace gravity with mg. Solve for tension, and we get ma plus mg equals tension. I'm going to go ahead and plug in my values. So the mass is 12 still. A is the acceleration of the object itself, not gravity. So we are accelerating by 0.6, then plus 12 times 9.8, and that should give me the tension. And just right off the bat, I do expect my tension to be larger than the previous because we are trying to accelerate upwards. So we need to be able to have a overall net force up. So I do get 124.8 newtons for this example. Okay, the last example is a 12 kilogram bucket held by a rope that is accelerating downward. So it is falling with 0.8 meters per second squared. So in this example, gravity is going to be larger than the tension. We should have an overall net force down. That way we accelerate downwards, and that does mean that gravity is going to be larger than tension. We do have a net force. We do have an acceleration. Tension is still positive. It's just going to be smaller than gravity. Replace Fg with mg. Rearrange for tension, and we get the same formula as before, which is not a surprise because it is the same situation. We have ma plus mg equals T. Plug in your values. This time I'm accelerating downwards. Don't forget to make that a negative 0.8 to show that we're accelerating downwards. For acceleration of gravity, we've discussed this before, but you really don't want to make it negative 9.8 because you've already considered that it's negative in your free body diagram. And so since you've already considered it negative, you've already subtracted it. Making it negative 9.8 is just considering that negative twice. And, from our math classes, doing a double negative makes it positive. So you don't want to do that. Okay, but with the acceleration of the object, we did not consider that was negative yet because that's not on our free body diagram. That's a net force overall. So we really did need to think about, okay, downwards would mean that that's a negative acceleration value. Okay, so I expect my tension to be smaller in this example. And that's a great way to check your work because sometimes you will mess up the negatives and positives. So first, just think about it logically. Should you get a bigger or smaller answer? And I expected a smaller answer than the original. The original is 117.6 and I got 108. So I did get a smaller tension than if there's no acceleration. That does make sense since it does need to accelerate downwards. Okay, let's try a more difficult example. Okay, it says two crates, one with a 4 kilogram mass and the other with a 6 kilogram mass sit on a frictionless surface, so we don't need to consider friction. The crates are connected by a light rope and a woman wearing golf shoes. And that's just so she can get traction on the ice. Since it's frictionless, if she didn't have some sort of shoes on that were grippable, then she would just start slipping on the ice. So that's all that was for. She pulls horizontally on the 6 kilogram mass with a force F, and it gives a crate an acceleration of 3 meters per second squared. Okay, so let's just kind of draw that out. So you have a 4 kilogram attached to a 6 kilogram, and then she's pulling it with a force in that direction, which we don't know. And overall, it's accelerating 3 meters per second squared. And we'll just say it's accelerating right. So that is a positive acceleration. Okay, so we do have a tension. We have an overall force. This first part A just wants the pulling force. So when you have multiple objects, there's several ways you can approach this problem. You could draw a boundary around a single object. So you could draw a boundary around 4 and do a F net equation on that. You could draw a boundary around 6 and do an F net equation on just the mass of 6. Or you could actually draw a free body diagram around all the objects and do a net force on that. Now, when you're deciding what objects you want to circle, think about what it's asking for. Here's asking for the force she's pulling with. So if she's asking for the force she's pulling with, I either want to focus on the 6 because it has that force coming out of it, or the total overall 4 and 6 together would be a good option because that also has a pulling force coming out of it. Circling just 4 would not make sense because if we circle just 4 and focus on the 4 kilogram mass, the only force coming out of that is tension, and that's not what it asked for. It asked for the pulling force. But what you'll also realize is when you try to go do 6, here, let me write it off to the side. So if we try to just focus on the 6 mass, you got MA. And then for the forces on 6, you have the pulling force heading right, which would be positive, and the tension force pulling left, which would be negative. And whenever you go to solve for the pulling force, you have MA plus T equals F. And then that does mean that we'll have to find tension, which is going to cause it to become multiple steps. We'll have to go focus on 4, find tension, and then come back to that. But the best option for finding the pulling force is actually doing both objects together. So if we circle both objects, 4 and 6, you'll notice that the only force coming out of it is that pulling force. The tension is inside that system, and we only want to focus on the forces coming out of that boundary or coming into that boundary. So the only thing crossing the boundary of both objects is that pulling force. Okay, so if we do an F net equation on both 4 and 6, you have mass, I'll just call it mass 4 and mass 6 because we didn't really do 1 and 2, times acceleration, and the only force is that pulling force. The tension is inside the system, it's not crossing that boundary. We only consider forces that are coming in and out of the system we defined. Okay, so 4 plus 6, both objects should be accelerating with that acceleration of 3. So it looks like my pulling force, she's going to be pulling both masses, so 10 kilograms in total. She causes an acceleration of 3, and so that would be a total force of 30 that she would have to apply. Okay. Part B says, will the tension in the connecting rope be larger than, the same as, or less than the force F? So if we think about it, the tension, think about what mass it's pulling. Is it pulling the 6 kilograms, the 4 kilograms, both? Is it pulling 10 kilograms? And then it makes the problem a lot simpler. If you look at the tension is really only pulling the 4 kilogram mass along, whereas she has to pull all 10 kilograms forward. So the tension should be smaller than the pulling force just because it's only pulling that 4 kilogram mass. And we can prove it with math. So if we want to know the tension, think about what object you would really want to focus on. For tension, look at mass 4. And that should give you the tension very easy because the only force coming out of that mass of 4 kilograms is the tension. So if we do an F net of just the 4 kilogram block, you just have one force, tension. That pulling force is not on the 4 kilogram block, it's on the 6 kilogram block. So you don't need to consider the pulling force at all. Okay, so with a mass of 4, it's accelerating with an acceleration of 3, just like the whole system. The tension should actually just be 12 newtons, which is smaller than my 30 newtons that the woman had to pull. Okay, here's an interesting example. We're looking at angles for the first time. So be careful with angles, right? We want to think about what's adjacent and opposite. But we do have FG pulling straight down. I know that for sure. We have T2, and we'll call this T1. And then it does give me an angle of 60 and an angle of 30. What I really need to do is break apart that tension into T2x, T2y, T1x, and T1y. Okay, so let's think about the x direction first. So if I'm looking at this x direction, T2x, think about the angle that it's giving you. It's giving you that 60 degrees up at the top of the triangle. Well, 60 degrees is actually, the x direction would be opposite. So I want to do the tension, and if it's opposite, we need to do sine of theta. And for T2y, the y is adjacent to that angle. So I'm going to do T2 cosine theta for the y. And the same situation would happen over here. We have T1 sine theta. And for T1y, we have T1 cosine theta. Okay, so it says a 5.5 kilogram ball is suspended from the ceiling by 2 strings. The ball is at rest, so we need a net force of 0. Is the tension in string 1 greater than, less than, or equal to string 2, and why? So if we look at it, just think about whether you want to look at the y or x direction, because there is an easier option. For the y direction, we have gravity and both tensions acting. So we have 3 total forces in the y direction, T1y, T2y, and Fg. In the x direction, I only have T1x and T2x. So if we look at the F net in the x direction, that will make it a lot easier. We want an overall net force of 0. T2x is acting to the right, so I'm going to make that positive. And then T1x is acting to the left, so I'll make that negative. Let's go ahead and move T1x to the other side. And it really just wants me to compare the 2 values. So if I could just make the replacement, instead of T2x and T1x, let's go ahead and make it T1 sine theta, T2 sine theta. And what we actually need to do is just compare the 2 angles. Tension 1 is going to be equal to tension 2 sine of its angle over the sine of the first angle. So let's go ahead and plug in values. Let's see what sine of 60, let's go ahead and replace that with 60, over sine of 30 would be. Okay, so sine 60 divided by sine 30. And it looks like T1 is equal to T2 times 1.73, which math is a language in itself. If you read that as a sentence, it's saying T1 is equal to T2 times 1.73 of T2's value. So T1 should be bigger than T2 if that's true. Okay, so it looks like the smaller angle is going to need a larger tension to compensate, which does make sense. You could have thought about it logically. We proved it with math. But having a smaller angle means tension is going to be bigger to compensate for that smaller angle. Okay, 2 blocks are attached by a rope to a wall. The child pulls horizontally on a second rope attached to each block. Below, both blocks remain at rest, so we have F net 0, and it's frictionless, so no friction. Then it says rank the tensions. So we're going to be ranking TA, TB, TC, and TD. But if we need a net force of 0, whatever's pulling right is also going to be pulling left. So if it's pulling 80 for the rope on B, it does need to pull 80 for the rope on A. In the next example, it does have a different mass. This one's 20 newtons, this one's 30, but remember, gravity and normal force act in the y direction. Tension is acting in the x direction. So just because one weighs 20 newtons and the other weighs 30, it's really not going to make a difference for tension because there is the x and y act separately. Now, if there is friction, that would start changing things because the friction is tied to the normal force. So having a different weight would affect the friction because the more weight you have, the more friction is caused. But it's frictionless, so the x and y have nothing to do with each other. So if TD is 50, then TC should also be 50. Okay, so for ranking them from greatest to least, A and B are both the same, but they're greater than C and D. Explain your reasoning. First of all, the FG does not affect tension. So I would want to mention that for my explanation. And it's also because there's no friction. If there was friction, that would change the answer. And then we also know that there should be an F net equal to 0. So A should be equal to B and C should be equal to D because of that. Okay, in this example, it says, will the man be able to pull the chain straight? Why or why not? Well, this one becomes pretty simple when you look at a free body diagram. What it's asking is, can this man pull the ropes horizontal, which this is what the free body diagram for that would look like. And just looking at it, you immediately know that this is not possible because the object needs to have an F net of 0. If there's a force of gravity, then there has to be a vertical tension to cancel that out. So if FG is there, there has to be tension in the Y to make F net equal 0. So having those chains fully horizontal does nothing to counteract gravity, and then that would imply that the object is falling, but he should be holding the chains. So those two things contradict each other. Okay, this next example, what will the spring scale read in the middle of the rope? Okay, so there's something important to remember about tension. The tension that the rope feels along each point should be the same. And another thing about spring scales is this hook end is the only thing that actually reads the force. The hoop does not read anything. And so the spring scale, whatever the hook is pulling, that's what it's going to read. So the loop end is not going to do anything. So if this weight is 100 newtons, the tension should be 100 since it's at rest, I'm assuming. Meaning that even if it's over the pulley, that spot would be 100. Same thing would happen over here. But remember, the spring scale is only going to read on the hook side. So just 100 newtons should be what the spring scale reads. Remember that tension is the same along the rope, as long as it's the same piece of rope. Okay, which leads me to my next example. So let's look at spot A. It's easier to think about that spot first instead of considering the whole picture. So at spot A, we have the force of gravity, which is 80 newtons pulling down. And so if this is at rest, then we need a net force of 0. So if it's pulling down down 80, then the tension should be 80 pulling up. So if we look at A, it makes sense if gravity is pulling 80 down, tension should be pulling 80 up. Same thing for C. I feel like C should be 80 as well. B is a tricky one. Some people think it should be 160. Some people think it should be 0 because one's pulling right, one's pulling left. But think about tension in a rope. If it's the same rope the whole way through, it has to have the same tension. So if I have 80 newtons at A and 80 newtons at C, then what must B if it's the same rope the whole way around? The tension should be 80 there as well. Okay. For D, we have 40, F, we have 40, E should also be 40 for the same reason. It's the same rope the whole time. So if you have tension of 40 on one side and 40 on the other, then it should be 40 in the middle as well. Okay, so that means that A, B, and C are all equal and greater than D, E, and F. And then just remember that tension is the same at all points along the rope. The only time this is not true is if the rope itself has a mass. Like if it were a super heavy rope, then the tension at the top of the rope is usually greater than the bottom because it's also having to take on the weight of the rope itself. But 99% of the time, our ropes are massless and ideal. So the tension should be the same throughout. It would have to specify that the rope has a mass and is bulky, and then that would change the way you think about tension, but that rarely ever happens. Okay, so this example, we have a lamp hanging from the ceiling. It looks like there's some sort of bar coming out of the wall that's keeping the lamp at that angle. And we see that force of the bar pushing to the right. So let's draw a free body diagram. We have force of gravity pulling down. We have the force pushing it out of the wall from that bar, whatever that is. And then we also have a tension at an angle of 70. Okay, so that would be my official free body diagram, but to do math, you actually would probably want to break that tension down into Tx and Ty. So look at Ty. Ty this time is opposite of that angle. So for opposite is a sine function. So we're going to do sine theta for that. And Tx is adjacent. So I'm going to do tension cosine of theta for x. And it says, what is a lamp's mass? So the lamp's mass is going to be tied to force of gravity. So I'm really trying to figure that out. I'm going to assume that the lamp is at rest. So that means the net force is 0, the acceleration is 0. So we have to make that assumption, but that's a pretty easy assumption to make. So if I want gravity, I'm going to focus on my y equation. That way I get the mass. Mass is tied to gravity, so I'm going to focus on the y. In the y direction, we should have a net force of 0. My tension in the y direction should be the positive, and Fg should be the negative. I'm going to replace Ty with T sine of theta, because that just makes more sense. And I'm going to replace Fg with Mg, just like we always do. Now I'm going to rearrange and solve for mass. So to do that, it would actually be better to move Mg to the other side to make it positive. So I have Mg equals T sine of theta, and then I'm just going to divide by G on the other side to just get M by itself. Now the only problem is I have the angle at 70 and I have G at 9.8, but I do not have tension. So it looks like I have to go on a side mission. And since I already looked at Y, let's go ahead and look at the X net force. Okay, so in the X direction, we have this force coming from the wall. That's positive because it's pointing right. And then we have Tx pointing left. I do know what F is, so I don't need to do any replacing for that. It says F is 36 newtons. For tension, I want to do T cosine theta. And then we're solving for tension. So I'm going to go ahead and rearrange. Tension cosine theta should be on the other side to make it positive. And then what I need to do is just do F divided by cosine theta. Okay, so let's go ahead and plug that in. So 36 divided by cosine of 70. And I'm going to go ahead and type that into my calculator. Or actually, you know what we should do? We should actually, what they wanted you to do on the AP exam is replace tension with F divided by cosine of theta. So let me go ahead and do that. And then I can go ahead and plug in my value. So F was 36 divided by cosine of 70 times sine of 70 divided by 9.8. Which really I should have probably put the cosine 70 on bottom. Just to make it look neater. So 36 times sine of 70 divided by 9.8 times cosine 70. And then we do get 10.09 kilograms for that mass. Okay, so just remember you have F net Y and F net at your disposal. So if you get stuck like we did with tension, then you just switch gears, focus on the other, solve for what you're missing, and then go back to the original problem. Okay, so we have a 35 kilogram crate being pulled with a force of 185 at an angle of 25 from the horizontal. The mu, so that immediately makes me think of friction. So we will have friction. The mu between the crate and the floor is 0.45. Determine the acceleration. Okay, so doing a free body diagram, we have Fg, we have Fn, we have this 185 force at an angle of 25 from the horizontal. And then we're also going to have a friction force. Remember that friction force is equal to mu Fn. And for this example, the normal force should be equal to the force of gravity. So really we have mu force of gravity, which will be better because we do have the mass, 35 kilograms. Okay, we need to break down this force into Fx and Fy. So for Fx, x is adjacent, so we're going to do the original cosine theta, since adjacent is cosine. And then for Fy, we're going to do F sine theta, since it's opposite. Okay, so if I want acceleration, I can do x or actually I can't do y. For acceleration, it should be accelerating to the right, and so I really need to do an F net x equation. I need to focus on the direction we're accelerating. Okay, so if it's moving in the x direction, that's what I need to focus on. I'm going to do MA. And then the x direction, to the right I have Fx. To the left I have friction. So Fx and then subtract friction because it's opposing that motion. Fx is actually F cosine theta, and force of friction is actually mu Fg. And then remember we replace Fg with mg. I am solving for acceleration, so I'm going to go ahead and move that mass to the other side by dividing by mass. And I think I have everything I need. So the force that we're pulling is 185 cosine of 25 minus, and then our mu is 0.45. Our mass of the crate was 35, 9.8, all divided by 35. Okay, so let me type that in. 185 cosine 25 minus 0.45 times 35 times 9.8 divided by 35. And then we do get the acceleration is 0.38 meters per second squared. So that's it for tension. It's pretty simple. You still use F equals MA. And the tension is just dealing with ropes. And there's a lot of angles when you're dealing with tension, which I try to do a lot of examples with angles. And angles aren't a big deal. Just remember for your free body diagram, the official free body diagram is everything that's in the red right here. But that green where I broke it down into FX and FY, that is not part of a free body diagram. That's just you doing side work for your math. So if they ask for a free body diagram, you keep the original vector at the original angle. And then when you need to go do math off to the side, you can do the cosine and sine functions. Okay, so that's going to be it for tension.